Well, I shouldn't necessarily ask a question that I'm not positively sure of the answer, but did this homework go a little bit faster than integrating?
Yeah.
Oh, yeah. Okay. All right. That's the answer I was hoping to hear, but you never know for sure until you hear it. Okay. We're going to just do a, we're looking at all these different tests. We're seeing whether series converge. And let's just finish up here on the alternating series where they alternate, the terms alternate between positive and negative. And we have an alternating series test to see if it converges. And the test is this, and for starters, let me point this out, that if you see this in the term -1 to a power, that is your clue that yes, indeed, you do have an alternating series. So that's going to be your clue, that you have that. Now, this will converge if the terms become successively smaller and smaller. So in technical language, that's if this b sub n plus 1 is less than the bn, which is the preceding term. All right, they get smaller and smaller. And then also you have to have this condition too, that these bn terms, as n gets bigger and bigger, they go to 0. All right, so those are the two conditions for this alternating series. And if both of those are met, then we can say that the series converges. Okay, so I want to look at this example here. Summation of, again, -1 to the n, so that's your clue, it's an alternating series of 3n divided by 4n minus 1. So first of all, yes, it's an alternating series. Okay, and then we have to ask ourselves, because we have to have the conditions present for the convergence, is bn plus 1 less than the preceding term? In other words, do they decrease in value? Question mark. Now, it's not immediately obvious to me that these bn terms decrease in value. It's not. So what you can do when it's not immediately obvious, you look at the corresponding function and get its derivative and see if the derivative is less than 0. Because if the derivative is less than 0, then the corresponding function is decreasing. So therefore, the series is decreasing. So we're going to do that first. So let's look at the corresponding function. And that's going to be f of x equals, and then for the n, you put an x, and you don't do the minus 1 here. That's not part of it. 3x instead of 3n over 4x minus 1 instead of 4n minus 1. Now we want to obtain, first of all, its derivative, which means that we're going to need to use our good friend, the quotient rule, to do that. So what do we have? We square the denominator, so in parentheses, 4x minus 1 squared. And then it's the bottom term times the derivative of the top term, so 4x minus 1 times the derivative of the top term, which is 3, minus, not a plus, the top term times the derivative of the bottom term. Derivative of 4x minus 1 is 4. Okay, so let's see what that numerator comes out to be here. Let's distribute. We have 12x minus 3, then minus 12x, all right? And then on the bottom, of course, we have 4x minus 1 squared. So the numerator, of course, we have a couple things that cancel out. So in the numerator, we have minus 3 over 4x minus 1 squared. Correct something in my notes. All right, so that's our derivative. Okay. Now, first of all, is the denominator ever going to be negative? No, because we're squaring, so it's never going to be negative, and we have a minus up above, so this thing is always going to be less than 0. It's a negative value. So we've learned then that the first derivative of our corresponding function is negative, so that means our f of x decreases, and thus our term that's related to that, 3n over 4n minus 1, decreases. So rather than just eyeballing it, doing a couple of terms and saying, yeah, it decreases, this is a more formal way to actually prove that it really does decrease for everything. Okay, so we've met that particular, so bn plus 1 is less than the preceding term. Now, the other thing we have to have in play here for the alternating series test is that the limit of the bn's have to go to 0. So let's look at the limit as n goes to infinity of our bn, which is what, 3n over 4n minus 1, and figure out what we get there. So what's the trick here to help me figure out what to have as this limit? We've used this on more than one occasion. What do I need to divide each one of those terms in the numerator and denominator by? Highest power of n, which is what? 1, n to the first power. We divide everything on top and bottom by n. Oops. So this is the limit as n goes to infinity of 3n over n on the top, 4n over n on the bottom, and minus 1 over n. Don't leave out any of the terms. Okay, so we've got some things that can simplify here, so let's do that. The limit then as n goes to infinity. Now on the top, 3n divided by n, the n's cancel out to a 3. On the bottom, 4n over n, the n's cancel out to a 4. And then we still have this minus 1 over n. Now that minus 1 over n, as n gets bigger and bigger, is going to go to what number? It's going to go to 0. Right. So then the 3 stays and the 4 stays. So my limit here is 3/4. Okay. All right, that's a problem here because it's not 0. Remember, for the, let me go to another page here, for the divergence test. What's called the divergence test. if we have a series A sub n, all right, if the limit of the A sub n's as n goes to infinity doesn't equal 0, and I want to also add this because I jumped ahead a little bit with this, or the limit of the A sub n's as n goes to infinity does not exist, then the series diverges. So this can be a very nice test to determine whether a series diverges or not. Okay. Well, in this case, our limit certainly doesn't equal 0, all right? So we're going to conclude that the series diverges. But I've misspoken here a little bit, so I want to clarify things. Here our an really equals the minus 1 to the n times 3n over 4n minus 1. Okay. That's really our an, the term of each of our original sequence. Notice that this minus 1 to the n keeps flipping things positive, negative, positive, negative. And we know that this part of it, we've already shown that this part of it goes to the number 3 over 4. So this limit actually goes to, it flips between a number close to 3/4, and then it flips to a number close to negative 3/4, then back to a number that's close to 3/4, then back again to a number that's close to minus 3/4. So it flips back and forth. And when a limit flips back and forth like that, it doesn't exist, because it has to equal one single finite number. All right? So this limit here does not exist, because it keeps flipping back and forth. Keeps flipping back and forth. So this particular alternating series then fails this particular test here. Basically the bn's don't go to 0, and also we could have just used the divergence test on this and not even use the alternating series test. Just using the divergence test, we see that the limits of the individual terms doesn't go to a single number, so it therefore diverges. And back to the alternating series test, since the limit of our bn terms is 3/4, since the limit of the bn terms does not equal 0, our second condition isn't met. All right. But in addition, then, we know that it has to diverge because of the divergence test. Those last terms don't go to a single number 0. Yeah?
Okay, this is kind of like a speed. We found that when we have bn is greater than bn plus 1, which one?
Okay. This is what we have here. This series has, okay, let's go, where's my original series? Here it is. Here's the original series. So this is, when n is equal to 1, it starts out as minus 1 to the 1 power times 3 times 1 over 4, 1 minus 1. All right. That's, let's see, what's the better way to say this? Let's go back up here. I'm sorry, I want to make sure I can. Here we have our alternating series. We got the minus 1 to the n minus 1, and it's multiplying something that we call bn. And notice here it starts out at positive b1, then minus b2, then positive B3, etc. Now I could keep going with this and then have, okay, we have a Bn where n stands for some positive number, all right? And then after that, the term after that is the next term, which is the next, has as a subscript, the next positive whole number, which is n plus 1. Okay? So therefore, the Bn plus 1, let's just do some examples here. If n were equal to 3, Bn plus 1 would be B sub 4, 3 plus 1. And we need that to be less than B sub 3. But let's move on. Let's say we're now up at 10. If n is equal to 10, the Bn plus 1, well, 10 plus 1 is 11, is B sub 11, has to be less than B sub 10. All right? The n is like a placeholder for any whole number. All right? What this means here, so therefore, when you say, what is the B sub n plus 1, well, that can vary depending on what number n you're talking about. But I want to impress on you that this means that this is the very next term of the Bn's after this one on the right side. Okay, so each successive term of the Bn's is less than the one before. All right? Yeah, B sub 11 is less than B sub 10. B sub 15 is less than B sub 14. They all keep decreasing in value. Does that help? That n terminology is, you know, it's a level of abstraction because that n stands for any whole number. So sometimes it can be helpful if you can just fill in some whole numbers like I did over here to kind of get a better idea of what that means. All right?
You know how, like, one's positive and then the next one's negative? What if it wasn't?
Okay, what if they didn't alternate like that?
Well, no, like, okay, one's positive and one's negative. What if because you said that you want the other one to be...
Okay, these B sub, in this notation up here, Jenna, these B sub n's are always going to be positive numbers. They're going to end up being positive in value. So we're taking something that's positive in value, and we're either multiplying it in front by -1, which will give us a negative term, or we're multiplying it in front by +1, which will give us a positive term. So these Bn's are always positive, so therefore when we multiply it by that different power of -1, we're going to get a negative followed by a positive followed by a negative. Does that help? Oh. Or you just say, yeah, it did. All right, so Bn's are going to be positive, so that gives us alternating. All right, so this thing, basically this example that I have here, this thing diverges. I mean, that's the thing that I wanted to say. So therefore, and it diverges because the limit of the AN. Now here the AN is the whole thing. -1 to the N, 3n over 4n minus 1. That does not exist. Does not exist. So therefore, the divergence test tells us it diverges. The other example that we looked at the other day, it met both of the conditions. The Bn plus 1 was less than the Bn, and the Bn did go to 0. So it met both of those conditions. So therefore, we can then have said, which we did the other day, that it converges by the alternating series test. Okay, both of those conditions have to be met for it to converge. Do we need to look at another example of an alternating series? Yes? No? I don't care?
I'm trying to remember what we did last time.
Okay. Let's look here. Actually, we can just look at something similar here. Maybe I should just do another one here. Okay, let's have a summation. We always want to have this -1 to either the n or the n-1 power. That indicates an alternating sequence. Let me put n-1. And then we have to have our bn here. And so let's have, what do I want to have? Oh, I don't want to mess with that. Okay, let's have something like that. Okay. All right. And so we want to know, does it converge or diverge? What does it do? All right. So the thing is, all right, we know it's an alternating series because of the -1. And let's check now. Does the Bn plus 1, is it less than the Bn? Now, again, this is the case where I need to look at the underlying corresponding function, because I can't tell offhand if that is true or not. So look at f of x equal to x squared plus 1 over x to the 4th plus 2. Ooh, I hope I didn't dig a hole with too big of a power here. So let's look at the derivative of this. Again, we have to use the quotient rule. So we have x to the 4th plus 2 squared in the denominator. Then we take the denominator, multiply it by the derivative of the numerator, which would be 2x, minus the numerator times the derivative of the denominator, which is 4x to the 3rd. And let's simplify the top here, okay? Let's distribute some stuff. So we have 2x to the 5th plus 4x. And then let's see, we have minus. Let me put a parenthesis here. Let's distribute here. This gives us 4x to the 5th plus 4x to the 3rd all over my denominator. All right, let's simplify this top here. 2x to the 5th minus 4x to the 5th. That's going to give me a minus 2x to the 5th. All right. Minus 4x to the 3rd plus 4x. All right. Okay. So I have this horrific kind of looking numerator here. And this is always positive. All right. And I think let's just be a little bit, wave our hands at this a little bit. This top part, look, we have a minus 2x to the 5th power, minus 4x to the 3rd power, and then all we're adding on to it is a 4x. So I think you can believe me that saying that for x bigger than or equal to 1, that thing's going to be a negative number. Because we're minusing x to the 5th, we're minusing x to the 3rd. Those are going to be big numbers, plus, and all we're adding on is 4 times x. Does it make sense that that's going to be negative? Okay. So it's going to be less than 0. So this thing is negative, less than 0. So we've shown, yes, Bn plus 1 is less than the Bn. All right. And then the other thing we have to show then is the limit of the Bn equal to 0? All right, so that is the limit as n goes to infinity of n squared plus 1 over n to the 4th plus 2. Is that, question mark, is that going to be equal to 0? And again, let's just do our old trick here, dividing by the biggest power of n, which is n to the 4th, right? So let's take n squared, divide that by n to the 4th. Let's take 1, divide that by n to the 4th. Then on the bottom, we have n to the 4th divided by n to the 4th, and then 2 divided by n to the 4th. All right, so let's clean that up a little bit. N squared over n to the 4th, that's 1 over n squared, plus 1 over n to the 4th, all over, now on the bottom, n to the 4th over itself is equal to 1, plus 2 over n to the 4th. Now, what are these three terms going to be going to that have the n squared and the n to the 4th as n gets bigger and bigger? They're going to all go to 0. So we're going to have 0 plus 0 over 1 plus 0, which is equal to 0. So therefore, the limit is 0. They get less than each other. So therefore, both of the conditions are met for this alternating series, and we can say up here, it meets all the conditions, thus it converges. Okay, all right. Good enough for... What we're going to go on to next, and that was section 11.5. 11.6, which is where? All right. It was here before class, so who took it? No. There it is. Touches my life at home a lot. Erasers disappear. Pens disappear, only to be found when I don't need them. Do you relate to that at all? Okay. The other day, I have this white eraser that I use a lot, and it was gone, and then all of a sudden, I got the calc book out, and all of a sudden it's like, it popped up, it just like magically, this white eraser suddenly materialized out of where, I have no idea. And so there it was. I don't know. Okay. Let's go on to section 11.6. All right, and I may not have reminded you guys to turn in the homework that's due today. Okay, 11.6 has a couple of topics in it. I'm just going to list the topics, and then of course we're going to go through it. It talks about something called absolute convergence. And then related to that, it talks about something called conditional convergence. And then we are introduced to two more tests. We're introduced to the ratio test, and these are the last of the tests, by the way. The ratio test and the root test. Okay. All right, so let's first of all look at what in the world do we mean by absolute convergence. Okay, so let's say we have a series, we have a series. We'll just call it the generic summation of a sub n, and goes from 1 to infinity. Now look at the sum of the absolute values of these terms. The sum of the absolute values of these terms. And so what we're talking about here is the summation, and now instead of just putting a sub n, I'm putting the a sub n, whatever that is, in absolute value notation, marks there, those two goalposts, as n goes from 1 to infinity. And so what this is, of course, is that this is the first term, absolute value, plus the absolute value of the second term, plus the absolute value of the third term, etc. So it's the sum of the absolute values. Now, let me bring in then the definition here of absolute convergence. A series, sum of a sub n, is said to be, quote unquote, absolutely convergent, if the series of absolute values converges. If the series of absolute values converges, i.e., the summation of the absolute value of the a sub n as n goes from 1 to infinity, if that equals a definite finite number L. Finite number L. Okay. All right. So that's what it means to be absolutely convergent. I have a question. If in the original series, if all of the terms happen to be positive terms, and if we find out that that particular series converges, the question is does that series converge also absolutely? Yes, and why, Will? Why would it converge? Why can you say it converges absolutely?
Because if it converges, then the numbers should be going to the, should all be positive anyway, or negative, and then you take the absolute value.
Right. Yeah. Yeah, because I told you that they're all positive anyway.
Yeah.
So if something is positive, it's equal to its absolute value, right? Because absolute value is always a positive number. So if something's already positive and it converges, then if I just put bars on it for absolute value, well, that's not going to make any difference because it's positive anyway, all right? So let me just put that fact down here. Fact, if all the terms are positive, if all the terms a sub n are positive, then a sub n equals its absolute value. And so if the sum of a sub n converges, then it also converges absolutely. Then it also converges absolutely. All right, so that's just if everything's already positive to begin with. All right. Now, let's look at some examples here for absolute convergence. And so so we want to take something that doesn't have all positive terms to it, all right? Let's look at the summation of -1 to the n minus 1 divided by n squared as n goes from 1 to infinity. Okay, now this is actually alternating series, right? We have the minus 1 to the power, so they alternate between positive and negative. Let me write a few of the terms out here. When n is equal to 1, minus 1 is going to be going to the 0 power, so that's 1. So that's 1 over 1 squared, n squared. And then when n is equal to 2, the minus 1 is going to be going to the first power, so that stays minus 1. And then 2 squared is 4. And then continuing, if n is equal to 3, we're back to a positive 1 on top, and then 3 squared is 9, etc. So that's what the start of this series looks like. Let's see if this is absolutely convergent. All right. So what we want to look at is this. The summation from n equals 1 to infinity of the absolute value of minus 1 to the n minus 1 all over n squared. But that's going to be just equal to the summation. So everything's going to be positive, so this is going to be just a 1 on top. And n squared is always positive, so it's going to be the summation of 1 over n squared when we do the absolute value. Now, is this then, first of all, what kind of series is it? It's a p-series. And does it converge or diverge? Okay, so it's a p-series. P is equal to 2, which is bigger than 1, so it converges. So the absolute values converge. When we do the absolute values, that does converge. Thus, we can say, thus, it converges absolutely. All right. Question. I guess we could just look at this, make sure we're okay with the other. Let's just not do the absolute value business. Does this thing converge without worrying about putting any absolute values on it? It's an alternating, without doing the absolute values, it's an alternating series. My bn's are equal to 1 over n squared. Okay. So my question is, okay, can I say that the bn plus 1s are less than the, let me rewrite that. Can I say that the bn plus 1s are less than the bn? Yeah. Yeah. I think we can be pretty safe to say that. And then is the limit of the bn's as n gets bigger and bigger, is that equal to 0? Yeah, because we have bigger and bigger squares in the denominator, so it equals 0. Yes. So therefore, this series converges by, I'll just put AST, the alternating series test, all right? Okay. Let's look at another example here to look at absolute convergence in that. Let's look at this series. It's another alternating series. N equals 1 to infinity, minus 1 to the n minus 1 now over just an n. Okay. So let's just write out a few of the first terms. When n is equal to 1, this will be a positive 1 over 1. When n is equal to 2, this will be minus 1 to the 1 power, so it'll be a negative 1 over 2. And then from there, it'll be positive 1/3, negative 1/4, etc. like that. So that's how the first few terms of it looks like. All right. So question, does this converge due to the alternating series test? Does that look like it might converge? Those are the two questions when we have an alternating series that we need to look at. So does these individual BNs keep getting smaller and smaller? Yeah, right? They go from 1/2 to 1/3 to 1/4 to 1/5, 1/6. But yeah, they keep getting smaller and smaller. And when I do the limit then, as the Bn is just 1 over n now. It's a positive. I want you to make sure you understand this. It's just 1 over n is our Bn. Just this part right here, that's our Bn. As that goes to infinity, n goes to infinity, does that equal 0? Yep, n gets bigger and bigger, denominator gets bigger and bigger. So the conditions, if both the conditions are met, so yep, it does converge by the alternating series test. Okay. Now let's put absolute values on this thing. So let's ask this question. Does it converge absolutely? So what we have to look at then is the summation of the absolute values of this, so that's -1 to the n minus 1 over n. And of course, that's just going to be always a 1 on top and an n on the bottom. N is positive, so that's what the absolute value is. So this is summation of 1 over n. I'll write out a few terms. This is 1 over 1 plus 1 over 2 plus 1 over 3, etc. And what do we know already about this series? It diverges. In fact, we can call it a p-series where p is equal to 1. If we have an n to the first here, p is equal to 1, so it diverges. And this, of course, we looked at this name before. This actually has a name. It's called the harmonic series. So what we have here is we've got this series. It converges by the alternating series test, but when we put the absolute values on it, it does not converge. Okay. There's a name for this kind of a series. If something if it just converges without doing any absolute values, but when we put absolute values on it, it doesn't converge, it's called conditionally convergent. That's that second thing that I had listed up there. So let me put this definition down here. If a series, we'll just do the a sub n, is convergent, so we find that it's convergent, just like we did with this last one, but it's not absolutely convergent, then we say it is, quote unquote, conditionally convergent. Conditionally convergent. All right, like that. It's a definition. You want to be mindful of what it means, just like you want to know what absolute convergence means. All right, so you want to know what that means. Okay. So there may be times when we might have a series that, yes, Jen?
On the test, so we're going to have to do different tests for each problem.
Maybe. Mm-hmm.
But, so we're going to have to do it for every single problem, because we're not going to know.
Okay, what you're saying is you're saying that for every single problem on the test, am I going to have to go through every single test? Is that what you're asking?
Yeah, kind of. The absolute value.
Mm-hmm. All right. The answer is no. And actually, that's what we go into in the next section after this. The next section after this is called strategies for series. What you have, and I'll just give you a preview of that. What you have to look at is, first of all, what form does the series have? Maybe it's a P-series, maybe it's a geometric series. You know whether those converge or not. Okay, or you should, okay? And then if it's not one of those, maybe it's an alternating series where you have the -1 to a power. If it's an alternating series, then you want to do the alternating series test. Okay? All right? And then there's more stuff after that. Okay, that's just a little preview. I don't want to give the whole lecture on it. But my answer to that is no, you don't, because not only are if you want to get practice on these by doing the homework, right? Because that'll give you more confidence then in being able later to see, well, what form does this have? And I don't have to do every single test. You'll get more confidence with that. And I'm going to give you some guidelines in the next section as to if it looks like this, then try this first, okay? That kind of thing. It's very similar to, dare I say, to the strategies that you had to deal with when you were doing integrals. But I'm hoping it's a little bit easier than the integrals. But again, with integrals, remember you had to look at, well, what is this, an x squared minus a squared, or is it an x squared plus a squared? You had to look at the form of it, right? In order to know where to go for it. So it's that similarity. All right. So what I was going to say here, if we have, and then we'll take a break, if we have a series that has both positive and negative terms, if we have a series that has both positive and negative terms, we may want to check if the summation of the absolute values converges. And why might we want to do that? Fact, I'm going to put an asterisk here also by this particular fact. If the summation of the absolute values converge, then the original series also will converge. Then the summation of a sub n equals 1 to infinity, will also converge. Let me just call this, let's call this the original series. Another way to phrase what I just wrote here for this fact is this, i.e., if a series converges absolutely, then it converges, let me just put in parentheses, the usual way. Right. So sometimes we might want to just check that. Does it converge absolutely? And if it does, we know it converges. So we're kind of clear on what that fact is there. Right. Let's take a 5-minute break before we go on that, okay? Was it as easy as 1, 2, 3?
I didn't really understand because it wasn't anything that was.
Yeah. Wednesday, I do have a recording.
Oh, cool.
Yeah, I do have a recording. I remember to push the recording button on Wednesday.
Where do I find these again?
Blackboard.
Right. Under the which tab?
Oh, it's actually right there. It's one of the main things on the left. I've got a thing that says links to recorded lectures. Click on that. Scroll down to the appropriate page.
I think I click on my other math class. For some reason, the summer one hasn't gone on my math.
Really?
Yeah.
It should be
It
off.
should
It should be off there already.
It
Yeah,
is.
don't.
I got 210
yeah.
and 220.
Click on the right. Click on this math class. Yeah. So therefore, you've got something to really look forward to this week, and you can watch that. You can listen to that video. Oh, just have some popcorn and just go to town. getting a message from afar. I'm hanging on your words. Very good. Thanks, Annalie. All right. I want you guys to remember something here about some of these tests that we've looked at here. Recall that, or remember that the comparison tests, the limit comparison test, and the integral test all required that the terms be positive. All require that the terms be positive. All right. So what do we do when we have a series in which some of the terms are going to turn out to be negative? So what do we do when some of the terms are negative and it's not an alternating series? And it's not an alternating series. Oops. Okay, that's what we're going to see in the next example here. To put it in a nutshell, this is what we're going to do. We're going to look at the absolute value of the term. We're going to see whether it can, and hope that it converges absolutely. And if it converges absolutely, we're good to go. It converges. That's what we're going to do. So let's look at this. Example, the cosine of the number n divided by n squared as n goes from 1 to infinity. Now this is not an alternating series. We're talking about the cosine of 1, the cosine of 2, the cosine of 3, 4, 5, etc. Some of those, because we know the cosine has positive and negative values, some of those are going to be positive and some of them are going to be negative. All right? But it doesn't alternate between every other term. So this is not an alternating series, but some of the terms are negative. Not an alternating series, but some terms are negative. So what we're going to do is we're going to look at this. We're going to look at the summation, n equals 1 to infinity, of the absolute value of these terms. Oops, that's not factorial. That's n squared. Sorry. All right. Now, from trigonometry, we know that the absolute value of the cosine is always going to be less than or equal to what positive number? 1. Right. Cosine goes between -1 and +1. So the absolute value is going to be less than 1. Before I do this, so the absolute value of the cosine of n is less than 1, or equal to. Therefore, the absolute value of the cosine of n over n squared is less than or equal to 1 over n squared. Okay? So, we're going to, the terms are positive. Terms are positive. Let's do the comparison test. All right. So, we have terms that are less than 1 over n squared. So So therefore, is the summation of 1 over n squared convergent? What kind of series is it? P series, P equals 2. P equals 2, so yes, since P is bigger than 1, it does indeed converge. So these are smaller terms than the other one, and the other one converges. So it converges by comparison, by the comparison test. And so, since it converges absolutely, we know that it converges the usual way. Thus, this series, cosine of n over n squared, converges absolutely, because the absolute values converge, and so it converges the usual way. All right. Okay. Yes?
The cosine of n over n squared, that's pretty different. So like from 1 over n squared, like what happens to the cosine? Does that matter?
What happens to the cosine? Where are you talking about? Are you talking about right here?
Yeah, you compare it to 1 over n squared, but...
Mm-hmm. Right. I used the fact, this is the fact that I used. I used the fact that the absolute value of the cosine, no matter what its argument is always going to be less than or equal to 1. And because of that, if the numerators are less than or equal to each other, if I'm dividing by the same thing that's positive, this is just algebra, then this implies that. Okay? What you want to do is you want to hunt for something that you know is convergent, that you can make it less than. And you use that fact from trig that absolute value of the cosine is always less than or equal to 1. So you can do that comparison. All right. So that, and you'll see something like this at some point in time. So that's a good thing to do if you have some positive, some negative. Let's look at the absolute values of it, see if we can compare it to something, and go from there. All right. Now let's look at actually one. Remember at the beginning of this section I said there were also 2 tests that we're going to be looking at. In fact, I think this is how I'm going to do this. This is because there's a lot of writing with this. The first test we're going to look at is called the ratio test. And this test is good for one of 2 things. It's good for determining absolute convergence, or it's good for determining whether it diverges. Okay, let's look at the test. It's got 3 parts to it. And what we look at is we look at the ratio of the following term divided by the preceding term. So this is how you write this in this notation. I look at the ratio or fraction of a sub n plus 1 divided by the preceding term, which is a sub n. I put it in absolute values, so I have the absolute values here. And I take the limit then of this expression as n goes to infinity. So we do a ratio with the succeeding term over the preceding term, absolute values, take the limit as n goes to infinity. Now, if this equals a nice number L that is less than 1, some number L less than 1, then I can go back to my original series and say it converges absolutely. which means that it converges the regular way. So the key here is this limit has to be some number less than 1. Not equal to 1, but less than 1. Then we have the case, the second case, again we are doing the ratio of the succeeding term over the preceding term. Okay. Taking the absolute value, taking the limit as n goes to infinity, and again, this equals some number L, but this time around, this number L is bigger than 1. Or we could have the case that this limit of this ratio gets bigger and bigger and bigger and bigger and actually equals infinity. Either case. L here is a finite number. If that is the case, then our series is divergent. Okay. Then finally we have the third case here, number 3. So again, we do the ratio, we take the absolute value, we do the limit as n goes to infinity. But this time the limit is exactly equal to 1. When this happens, this test is inconclusive, i.e. it tells you nothing. It does not lead us to a conclusion about whether it converges or diverges. It just leaves you hanging, okay? So we have 3 scenarios here with this. That limit can be equal to a number less than 1, in which case it converges. It can be equal to a number bigger than 1, in which case it diverges, or it can be equal exactly to 1, in which case it tells us nothing. Okay, so I want to look then at this example here. Let me write this here. Summation of minus 1 to the n power of n to the third over 2n as n equals 1 to infinity. All right. Okay. Okay. For starters, what kind of series is this? Alternating, absolutely, it's alternating. It's got the minus 1 to the n power. Let me say this. We could use the alternating series test to test for convergence. Okay, we could do that. Okay, but we're not going to do that one for this particular example. We're going to use the ratio test. All right, and in a couple minutes I'm going to give you some times when you really want to go to the ratio test as your first choice. So we're going to do that. All right. So therefore, what we're going to look at then is we've got to look at this. The absolute value of a sub n minus 1 divided by the absolute value of a n. Now, what is our a n here? Our a n is this term here, minus 1 to the n power n to the third divided by 2n. That's our a n, the whole term there. Okay. Now, first of all, when I put absolute values around this thing, what's going to happen to this thing right here, that minus 1 to the n power? Remember, that flips either between negative 1 or plus 1, negative 1 plus 1. If I'm looking at absolute values, what's going to happen to that? It'll just say plus 1, right? Because absolute value is always positive. So I can really, for absolute value purposes here, I can ignore that minus 1 to the n plus 1. It's always going to be, for absolute value, equal to 1. So basically, the absolute value of a sub n, then, is going to be n to the third over 2n. Remember, these n's are 1, 2, 3, 4, etc. They're all positive numbers, okay? So n to the third is going to be a positive number, and 2 to the n power is also going to be a positive number. So this is positive. So therefore, it's equal to the absolute value, all right? Are we okay with that? All right. So let's look at this ratio then here. Okay, first of all, I've got to put a to the absolute value of, this is going to be the absolute value of a sub n plus 1. I can separate it out like this if I like, over the absolute value of a n. And now the absolute value of a n plus 1, for this one, I have to put in n plus 1 instead of n. So you have to be a little careful here with this. This is n sub 1, n plus 1. So for this, instead of n to the third, I'm going to put n plus 1 to the third power, all right? And then instead of dividing by 2 to the n power, I'm going to divide by 2 to the n plus 1 power. So every place there's an n, I plug in an n plus 1 to indicate I'm working with that term. And then big line here divided by my absolute value of a sub n. Well, I had already written that out. That's n to the third divided by 2 to the n power. All right, so we have this big, ugly looking thing which will quickly become not so ugly. All right? We have a fraction divided by a fraction. Remember what I said before, when you're dividing by a fraction, it's the same as multiplying by the reciprocal. So I can write this thing, instead of that huge thing, I can write it like this. Let's write the top part, n plus 1 to the third power over 2 to the n plus 1. But now, instead of dividing by that lower fraction, I'm going to multiply by the reciprocal of the lower part. 2 to the n divided by n to the third power. All right? So that's your first step. Are we all on the same page with that? All right, now stuff is going to cancel out or simplify. Let's look at the powers of 2 here. This is like 2 to the n power, but this is 2 to the n times 2 to the 1 power. When we have n plus 1, that means we can separate it out as n for our one exponent and 1 for our other exponent, right? Because we add the exponents when we multiply with the same bases. Now, so what can cancel out? I've got a 2 to the n up here, and I can cancel out the 2 to the n in the denominator. So I'm still left, however, with a 2 in the denominator. So let's write this as 1 on top, 2 on the bottom. I've simplified that part of it. We okay with that? I still have a 2 in that bottom. Now we have this n plus 1 to the third power divided by n to the third power. Okay, they're both being taken to the same power. So I can put those in one set of parentheses and put the whole fraction expression to the third power. If they're both being taken to that power, I can just go on and do that. Everybody okay with that step? All right. Then I do my trick here. I'm going to divide every term in this thing by the highest power of n, which is n to the first power. So this is going to be 1/2. Then I've got my big parentheses is taken to the third power. That's going to be n over n plus 1 over n, all divided by n over n And some of you won't even have to do necessarily that particular step to be able to write it like this then. In the parentheses then, n over n is 1 plus 1 over n, all divided by 1, and that's taken to the third power. This is the kind of manipulation that you frequently have to do for some of these problems. Question on just what I did there. First of all, we have the same power here, so I just put it as one expression with that same power. Then I divided by the biggest power of n. Biggest power of n. And so I ended up with what I have there at the bottom. Now, remember, this is as the limit. So what are we doing here? We're doing the limit as that n goes to infinity. So we have 1/2 times 1 plus 1 over n, all divided by 1, to the third power. So that inside that parentheses, we have a 1, we have a 1, and we have a 1 over n. So what's going to happen to that 1 over n as n gets bigger and bigger? Right, it goes to 0. So that stuff in the parentheses goes to 1 over 1 to the third power, and then we have the 1/2, don't forget the 1/2 that's in front of it. So this limit then is 1/2 times 1, or 1/2. All right? That limit then is less than 1, so it converges absolutely. So let me write this here. Since the limit as n goes to infinity of our absolute value a sub n plus 1 divided by a sub n turns out to be equal 1/2, and that's less than 1, then our original series, which was what now? Minus 1 to the n power, n to the third over 2n, converges absolutely as n goes from 1 to infinity by the ratio test. All right. And since it converges absolutely, we can also say it converges in the usual way. Also, it then converges in the usual way. Okay. So that's my first example here with ratio test. There is some algebra involved with this, with some doing and exponent stuff that I hope we're going to get clear on if we're not completely clear on right now. Anybody have any questions on that one at the moment? Actually, for a second, though, let me actually go back to this one. I don't want to, let me just write it again, because I just want to show here minus 1 to the n to the third over 2n as n equals 1 to infinity. I'm not going to do the whole thing, but I want to ask you this. Do you think this thing might converge if we just do the alternating series test? Because it is an alternating series. Any thoughts over there in Eureka and Lafayette land?
Well, it says that it converges the usual way.
Well, we already found out. Okay, let's pretend we just didn't do what we just did. All right? That's what I'm saying. Do you think it will converge with the alternating series test if we had just done that? So, Nikesha, I think you're saying what now?
What?
Will it converge using the alternating series test?
I think it might be a little bit more blinded.
You think it might be a little hard to do the mechanics of the test? It will converge using the test, but the mechanics of it might be a little tricky. Because remember, we have to find out if the b sub n plus 1 is less than the b sub n, which means that we have to look at the underlying function, x to the third over 2 to the x, and see if its derivative is less than 0. All right. Not that bad, but it could be a little tricky. All right. All right. And also the limit as n goes to infinity of n to the third over 2n, we want that to be 0. I think this is a good question. What tool that we've had could we use to determine that last thing? What's the limit of the top part as n gets bigger and bigger? Just the top part. Yeah, L'Hopital's rule. This, if we then look at the corresponding function, x to the third instead of n to the third over 2 to the x, this is an infinity over infinity case. We can use L'Hopital's rule, and we will find out that it's 0. I think we have to use L'Hopital's rule a couple of times in order to do this, but we will find that the limit as x goes to infinity will equal 0 using L'Hopital's rule. All right? Okay. Equals itself times the natural log of, very good. Well, the chain rule isn't going to do anything here because it's just x on top. Okay. So this is the derivative here of 2 to the x. Yeah. All right. All right. Let's proceed onward here. We digress, but I wanted to kind of look at that. All right. Let's look at another example with the ratio test. Okay, so here we have the sum of n to the n power divided by n factorial as n equals 1 to infinity. All right, so our a sub n here is equal to that n to the n power divided by n factorial. All right. Now, there's an easy way to do this one and a hard way to do it. Actually, the ratio test here is going to be the hard way to do it. But I'm just going to go through it just to show you the kinds of stuff that are involved. Let's try the ratio test. And don't get freaked out by some of the algebra that you're going to see, okay? Try not to. Okay, we need to look at that absolute value of the a sub n plus 1 over the a sub n. Oh, I'm sorry, I forgot to put here. Oops. Never mind. So, all right. So actually, all of these terms are positive anyway, so the absolute value isn't going to make any difference. So now for a sub n plus 1 on the top, I have to plug in n plus 1 every place there's an n. So what do I have here? I have n plus 1 raised to the n plus 1 power divided by n plus 1 in parentheses factorial. Every place there's an n, got to replace it with an n plus 1. And then I divide it by my a sub n, which is just n to the n over n factorial. So that looks pretty ugly. Let's try to remember again, we're dividing by a fraction, so that's the same as multiplying by the reciprocal. So that's going to be the n plus 1 taken to the n plus 1 power over n plus 1 factorial times, now do the reciprocal of the bottom. So that's going to be n factorial over n to the n. All right. All right. Can I simplify some stuff here since I have a factorial on the top and a factorial on the bottom? A lot of stuff is going to cancel out right there, right? We all know that n factorial is where you multiply n by all the numbers that are less than, all the whole numbers that are less than it, right? And n plus 1 factorial, we just have one more number that we're multiplying in front, right? So what does n factorial on top and n plus 1 factorial on the bottom simplify to? Yeah. Now, not quite. Actually, n plus 1 factorial, you're right. Jordan. So n plus 1 factorial, you can look at it as n plus 1 times the factorial of all the lower numbers, right? So it's n plus 1 times the n factorial. And then we have that n factorial on top. So the n factorials will cancel out, and so what I'm left with, though, is a number n plus 1 on the bottom still. All right. Now, I then have, let me just put a 1 up here as a placeholder. Now I also have n plus 1 to the n plus 1 power. Well, let me write that as n plus 1 times n plus 1 to the n power. Okay? This just means I multiply n plus 1 by itself, n plus 1 times. Well, I can separate that apart as taking it to the first power times taking it to the n power, because you just add the exponents together. Does that make sense? Does it make sense?
It does, but then I never saw it.
Okay, well, right. Well, it's good. Now you can start to look at it a little bit differently. And then we have still on the bottom n to the n factorial. Now let's look at what we've got here. Is there anything that can cancel out now? Top and bottom. Yeah, n plus 1. Got an n plus 1 on top, got 1 on the bottom. Let's get rid of them. So what are we left with now? We're now left with just the n plus 1 to the n power over n to the n power, like that. Say, oh, goody. Well, they're both being taken to the same power, so let me make one big parenthesis and put inside the top, n plus 1, and the bottom, n. All right? Just doing what we had done before, because they're both taken to the same power. Now, let's simplify this middle part here. If I divide everything by n, I'm going to come up with 1 plus 1 over n over 1, and then that's all being raised to the nth power. Or another way of writing this then is 1 plus 1 over n raised to the nth power. So this one, now, I think this illustrates the process. I don't think I'd want to give you something like this on an E-class exam, but I want to just show the process here of this gradually simplifying and canceling things out. Now remember, we take this limit as n goes to infinity. We finally have simplified this whole thing and got that. So we look at the limit of 1 plus 1 over n to the nth power. And guess what? This actually equals something that we know about. Anybody want to hazard a guess as to what this is going to equal? And it's not 1. It is a 1 to, yes, we can figure this out with the Hoppe-House rule. It is a 1 to infinity case. So we can do it with using the rule. I'm going to just bypass that. That's an interesting thing to do, though. But what we're going to end up getting is E. 2.718 ... That's what this is going to equal. I want you guys to remember this. All right? That little thing. The limit of 1 plus 1 over n in parentheses raised to the nth power. When you do the limit, it equals that nice little number E. Okay?
Does it come up often?
It might come up every now and then that you might want to know it. All right? Because it will come up, I know, on the homework. All right? So it's something that you then don't want to hunt around for. You just say, oh yeah, I know that this equals E, so I'm going to then put in E. Okay, so this equals E. Well, so therefore we found that the limit of our ratio here, a to the n plus 1 over a n, we've gone through this whole process, and it equals the number E. Now, is E bigger than 1 or less than 1? It's bigger. It's 2.718. So therefore, the limit here of this ratio is bigger than 1, so it diverges by the ratio test. All right. Now, this is the hard way to do this problem. We all remember the divergence test, that if that limit of a sub n of our term doesn't equal 0, then it diverges. Right? That's the divergence test. Well, let's see what we get here when we look at this divergence test with this particular series. Okay, our a sub n is equal to n to the n power over n factorial. Well, let's write this out a little bit. The top is n to the n power, so the number n is being multiplied by itself n times. That's what it means, n to the n times. And then that's being divided by n factorial. So let me write n factorial like this. 1 times 2 times 3 times 4 ... times n. So that's what that term looks like when we just expand it out to represent what it really is. Now, this number right here is equal to 1. All of these other numbers here, when we just look at the top over the bottom, are going to be less than 1. All right? I'm sorry, they're going to be greater than 1. Because this is going to be bigger than 1. I'm sorry, I should have. That's going to be bigger than 1. That's going to be bigger than 1. All these are going to be bigger than 1 as n gets bigger. So all of these are bigger than or equal to 1. So this whole thing is going to be bigger than n over 1, that very first item there. So as n gets bigger, a sub n is bigger than the number n. So can you see how that works if you just look at each individual fraction in that? They're all going to be bigger than 1, except for this very first one, we have n over 1. So it's going to be, the whole thing multiplied together is going to be bigger than n over 1, if all these other things are bigger than 1. Okay, as n gets bigger, a sub n then is bigger than the number n. So what would be the limit of a sub n as n goes to infinity? What could it be? If that individual term a sub n is bigger than any of these number n's, it has to be infinity. That's all it can be. Those a sub n's are going to get bigger and bigger and bigger and bigger because they're each bigger than the individual n's. So therefore, since, just using the divergence test, since the limit of the a sub n doesn't equal 0, then I can say it diverges by the divergence test. Now that process there looks a lot easier than the process here, all right? And we arrived at the same conclusion. All right. Now, I'm going to tell you now when it is you want to use this ratio test. So this is something you want to remember. The ratio test is usually, I'm not always going to say 100% of the time, but usually good to use if the terms of the series either have factorials in them or a constant number raised to the nth power. If the terms of the series contain either a factorial, in other words, n factorial, or a constant raised to the nth power, i.e. something like 3 to the n, that type of thing, all right? So we're talking about, let's see, I think actually one of the ones that we had done earlier here, let's see, from earlier, basically let's look at n to the third power over 2 to the n. Let's just look at it this way. All right. This term here, it has a constant raised to the nth power, this 2 to the n right here. That's an indication that you probably want to use the ratio test, all right? Okay, actually, the original one was -1 to the nth power. So that means you might want to look at the ratio test like that, okay? But also if it has a factorial. So when you go through and do the homework for this coming week then, and you see something, terms that have a factorial in them, or a constant raised to the nth power, if nothing else is coming to mind to work, you then want to think of using the ratio test. Okay, so let me make sure. That can just give you a hint that this is something you want to use. And the last thing I just want to talk about today is this, that sometimes this ratio test doesn't work. All right. For instance, if we look at the summation of 1 over n squared. Now, we know already that this thing converges. It's a p-series. We know it converges. It's a p-series with p equal to 2. But let's see what happens if we would try the ratio test, all right? What if we tried the ratio test? All right. So we have to look at here the ratio of those two terms here. So look at absolute value of a sub n plus 1 over a sub n. And of course, so our a sub n plus 1 is going to be 1 over, instead of n squared, it's going to be n plus 1 in parentheses squared, divided by, and our an is 1 over n squared. So we have to use that n plus 1 instead of n. Okay, this one isn't nearly as ugly as a couple of the ones that we've looked at already. So this simplifies to 1 over n plus 1 in parentheses squared times the reciprocal of the bottom one. So times n squared over 1. Okay, so this can be written as n squared on the top and n plus 1 squared on the bottom. They both have the same exponent, so I can put it all under in a side of parentheses, n over the n plus 1, and put the square on the outside. Now, when I divide everything on the inside here by n, I'm going to get 1 over 1 plus 1 over n in the parentheses squared. So doing that, and we know that this 1 over n is going to go to 0. So this limit, as n goes to infinity, of my ratio is going to equal 1 squared, which is equal to 1. When the limit is equal to 1, the ratio test itself is inconclusive. Of course, with this particular series, we didn't even have to go there to the ratio test. We already knew that it was a convergent p-series, so we didn't have to bother. But I just wanted to show, in this case, what happened, and it was inconclusive. All right, we shall finish Forge on again next time, and have a good weekend. Let's put cards in tonight and tomorrow, right? What?
The last day of my nature writing.
Oh, the nature writing. Oh, that's good.
There. Where is it?
Unreal class today.
It's on. Yep, and it's
thanks, Sam.
Now we gotta.
Oh, that didn't work. Anyway.
Our final essay is to read a book and quote what other people have about the book. And they're all crazy. Yeah, I've done a lot of times. 2000, it should be easy. You should make them all like 2,500 words. I know.